Good evening. My name is Claire Idstrom, and I'm an event coordinator here at Town Hall. On behalf of the staff at Town Hall Seattle and the Institute for Systems Biology, it's my pleasure to welcome you to our presentation with Ginny Ruffner and Dr. Jim Heath. Thank you.
Thank you so much. I'm broadcasting, right? Okay. It's an absolute pleasure to be here. I think over the past 3 years, I've probably hosted maybe 10 town halls, and this is the first one to do in person. It's phenomenal to do it in person. I am so happy. And I'm even more happy because I get to do it with Ginny, my great friend Ginny Ruffner. So for those of you who don't know Ginny, there's no one here that doesn't know Ginny. But as you all might know, she currently has an exhibit going on in the Bainbridge Art Museum, and there's a retrospective book of Ginny's artistic life. And the Bainbridge folks are over there. As I'm the president of the Institute for Systems Biology, and we're a nonprofit research organization that studies wellness. We study cancer, basically the fundamental biology of many human conditions, but from a systems perspective. And there's more information over there. So with that out of the way, it is absolutely fabulous to be here. So Ginny and I, for the past more than 3 years, every Sunday, we have dinner together and we play poker. There are several folks in the room that have come by on occasion and play poker with us. But when we see each other on Sunday, I always ask Ginny, what did you learn this week? And she asks me, what did I learn this week? And even though we're good friends, it is kind of a pressured question because you actually have to have a good answer. Ginny has very high standards. But over the past 3 years, as we've been doing this and beginning to understand a little bit about, I understand a little bit about her art and she about the science we're doing. And she's always been a science fan and I've always been an art fan. But I haven't been able to really explore in the kind of depth I have with Ginny what the artistic creative process is and how that contrasts against the scientific creative process. And in fact, I think until we decided to do this, we probably didn't have a good way to verbalize it. And I'm not even sure we're going to do a good job tonight, but we're going to try.
Yeah, Tiffy.
I'm not sure if I'm advancing. Am I advancing? Okay. Yeah, so that, I suspect I'm the cow. And I'm not advancing though. Or maybe I can't see what the advancing button is.
I can do it.
Okay. Okay. So, I don't think talking about science and art together is very original. What do you think?
That was an old topic, but we'll do it new. Can you hear me?
Yes.
Good.
Better also put your screen is down low.
Okay.
So we can see your mouth.
Okay.
So something that we had thought about in terms of trying to provide a theme for how we think about science and art together is that each of us are interested in creation stories. But there's a difference. As a scientist, I tend to look for patterns, and we'll talk about that because I want to walk through in a simple way and then with a little more sophistication on how I think about patterns, how I try to look for the underlying physics behind those patterns, and if I understand that well enough, to control and go back in the laboratory and alter those patterns to show that you can do something that you predict.
And Jim's right. creativity in art and science often was very similar, and actually it often starts in exactly the same way, by paying attention, asking questions, and then making up stories. And that's where the difference comes in. And then there are two reasons I can think of why artists and scientists' stories are different. One is artists ask really different questions, and two, the scientists have to prove all their stories. We don't have to. It's a great gig.
But the thing that whether I have to prove it and she gets to make it up, which is absolutely true, and that's I think there's a tension there, but there's also a complementarity there. It all starts, I think, the most important thing is to be curious and to notice. And so I'm going to walk you through just a way that, as a scientist, I would look at something, and then how the thought process there applies to something more sophisticated. And I'm going to start with simply talking about how Ginny and I might have a conversation. And so if we had a conversation and we're at a comfortable distance, that's great. But if I moved really close up into Ginny's face, she's going to push me away. And if I go too far away, gradually, she's not going to actually know that I'm there, and that conversation's just going to fade off. And you can represent that by this energy curve. I show an energy versus distance, and there's a minimum there, which is the place at which we're most comfortable talking, and it gets steep as we get too close together because that's just fundamentally uncomfortable. But it only gradually decays as you go in the other direction. So, next slide. So if I just modify that a little bit, it is amazing how much can be explained. And so all I've done is I've said, at some far distance, I've added a repulsion. So now I have this attraction at this comfortable speaking distance. I have a repulsion if we're too close, but now if we're too far away, I add another repulsion. And that's just how you describe social gatherings. So if you look at the bottom right of this, you'll see I've highlighted, there's maybe 4 or 5 groups of people talking. And I've highlighted 2 of them. I think one's a group of 3 and one's a group of 5 or so. And they're at comfortable speaking distances. But so those conversations don't interact, those groups separate. And if you actually looked above that room, you would find these groups are sort of evenly distributed. And if we break up from this town hall, start having wine over there, you'll find that same type of structure will exist. And that's because you don't want the conversations to interfere, and so the groups will repel each other, okay? And if you take that to the sort of extreme level, you get order. You get, in fact, a high degree of order. And this is obviously artificial, but it's designed because of those competing interactions of wanting to bring people together, but also wanting to keep people apart, wanting to have separate conversations. And when you have such competing interactions, structure emerges. And whether it's the structure of a tree, whether it's the structure of a group of people, whether it's the structure of the cells that line your intestinal colon, every time you see structure, almost always it's because there are interactions competing. And as a scientist, one wants to think, what are those forces that are keeping things together or pushing things apart? And if I can understand those, can I come in and engineer them for a different purpose or to make a different structure? That's the essence of science. So what do you think when you see?
Well, of course, I noticed that really elegant rhythm of the tables and chairs but I almost can't see it for that god-awful carpet. And so the competing interactions that I think about are in the designer's mind, probably competing interactions between improving maintenance and beauty. And looks like maintenance won.
I think you're right. I didn't even see the carpet till Ginny pointed it out. Yeah. So this is, I think, if you actually looked at this at low resolution and you looked at the last picture at low resolution, they look the same. Okay? But this is the cytoskeleton of a sea urchin, very different length scale. And the competing interactions here are, you need a flow through for nutrients, but you also need structural integrity. And a phenomenal question that a scientist might ask would be, these are inorganic structures. There's silicates and calcium carbonates and things like this, and yet they're built with organic proteins and encoded by DNA. And so, first, what is the molecular machinery that builds a structure like this? And what is the DNA software code that puts in this type of periodicity, and can it be manipulated so you could maybe make linear structures or, uneven structures or anything? Can you alter it? The next slide is just another example just to show you that these things pop up in nature all the time. This is just, these are little tiny particles, actually just two different sizes of particles, synthesized in the laboratory, but allowed to do what they will on a water surface, and you get these egg structures. And once again, if you looked at it at low resolution, it looks like the banquet hall. And the competing interactions here are basically repulsions against the water, because these are hydrophobic particles, and attractions between the particles themselves that differ because there's two different sizes of particles. This is absolutely modelable, and if you wanted to, you can go back in the laboratory and redesign this and make it form completely different structures, because this is, you understand the physics, you understand how to control it. I think, Jenny, when you look at this, you see something different, though.
Right. My question about self-organizing an organism is what is in that space, that they're spacing themselves, they're positioning themselves between, and this sculpture is called what's really in the space between integers. Do you remember in the 5th grade when you learned that there's infinity between integers? Well, my story is, as an artist, I get to make up stuff. And if there's infinity between integers, there has to be something in there. So I get to make it up.
So this is another example of a naturally occurring structure that's periodic, and that periodicity emerges because of competing interactions. These are fish scales, and the competing interactions are combination of protection and flexibility to allow the fish to swim. You can imagine if that competition didn't exist, you might have one big scale. That's a clam, not a very good swimmer. When I look at this, again, it's intriguing to think about what are the natural organic molecules that are engineered by nature through Darwinian processes and selection to construct a remarkably elegant structure like this. But I think, Jenny, you look at this and you see a different story.
Well, I definitely noticed the beautiful pattern and the play of light, but then I asked different questions. This is called The Birth of Caviar. Thinking about the origin stories of caviar, haven't you always wondered thought about the first person to eat caviar. He must have been really hungry. And then also, how did caviar come to attain the status that it has? I'm really curious about that as well. Another sort of bizarre interest of mine, that old joke, why did the chicken cross the road? I mean, it's not funny, and yet we all know it. How did it evolve? Where did it come from? It's, how did humor itself evolve? As an artist, I get to answer that question. Oops. And then thinking about making up creation stories themselves, the creation of creation stories. This piece is about, it's called Melting Evolutionary Theories. It's kind of a visual list of various creation stories. There's, of course, the Adam and Eve and the serpent, and dinosaurs, and that old chicken crossing the road again. But another creation story, this is called the invention of games. And I was wondering about why are those 4 shapes on all the playing cards? Why are they usually red and black? Why are they pretty much the same size, the same weight? So I was thinking about our love of randomness. There's the bingo hopper in there. And our love of risk. There are the random fruits from the slot machine. And our love of prediction, that graph line in the rear. What do you see, Jim?
Well, I got to say, I didn't plan to be Ginny's straight man tonight. But I think that's kind of how it's working out. You didn't warn me. When I look at something like this, I, as a scientist, one can't help thinking about, the games as a class of activities are intrinsically competing interactions. You have cooperation against competition, and that way of thinking is essential to so many fields. It's essential to economics, but it's also a way that one can model the diversity of the microbiome, as an example. And you have many microbes in your gut that are all living and cooperating with one another, but they're also in competition for nutrients. And you can model that type of behavior with game theory. And so I see the microbiome.
I see them competing right before our eyes.
So something that Ginny and I have also had a lot of discussions on is scale. So when you look at ordinary, everyday objects, and my fascination is looking at those objects down, how they behave at the molecular scale and the nanometer scale. Ginny's fascination is just change the scale and get a new story.
And often if you take an everyday object and make it larger, change it. You'll notice it a different way. You can change it into an art object, particularly if it moves unexpectedly. This is actually just a couple blocks from here on the corner of 7th and Union.
So I'm going to tell you, I give you just some feeling for how I love scale, a different story. This is something that we encounter all the time. It's just water on glass. But if you were paying attention to the first few slides, you're looking at this and you're thinking, there's competing interactions here. There's droplets, they're separated by a certain distance, there's a limited size range of the droplets, and you'd be exactly right. These droplets on water are, in fact, there's a tension and there's also an attraction between the water molecules themselves. But if you take a nominally dry surface, like the surface of the stage or what's on your chair or even your skin, and you look with any kind of a spectrometer, you'll find that that's covered with water as well. And so water does very different things on a nominally dry surface than it does on a nominally wet surface. And if you look at the atomic scale, what you find is that water on a surface like the stage actually exists at room temperature as ice. Very striking. And those ice crystals are just one water molecule thick. That's what you're looking at, an image of it here. And they're in tension with the underlying substrate because they want to form a crystal, but that crystal is out of registry with what's underneath. And so that causes that ice to break up into a pattern that has a certain finite size and a certain amount of predictability. The point being is that whether you take art or everyday objects and change their scale, or whether you take everyday objects that you normally encounter and you change their scale, the physics changes, the perception changes, and the story changes.
And as we said in the beginning, art and science can happen when you begin to look at things in a different way and not in their usual expected uses or the usual scale. When that difference is accepted and celebrated, art and science can happen.
Oh, don't go forward. No, go back. I got to say something about this. Because, having, this is the point being that a novel perspective is valuable, that actually adds a tension and an excitement to science as well. And in fact, the institute I lead, the ISB, is designed specifically to promote that type of tension. If you go to most science laboratories and universities and you walk through the laboratory, it has the feeling of a research motel. Now you get to be the straight man. That's good. You walk down a hallway and there's labs on either side. By design, the ISB, we have it completely open. And we have physicists, and I'm a physical scientist by training who does biomedicine now. We have engineers, et cetera. And they all have different perspectives on maybe a common set of problems that you're working on. And it's out of that, just like out of the conversations that Ginny and I have, that new things come. And I think that's very hard to teach, but it's really, really important.
Mm-hmm. Another example of that are, for example, looking at genetic engineering with a different eye, looking at it to not increase profit, but perhaps to increase beauty. In this case, its name of this piece is botanical scales for hornflower. What if you could genetically engineer flowers to make music? What would it be that would trumpet flowers make horn music? What would it sound like? What would the scales look like? Or what if you could see forces? What if there's a force that shapes seashells? And now, and we could see it, would that force carry the implications of the colors of the seashell that it was going to make, or of the shapes that was going to create?
Right. Exactly. So I think whether you're trying to make a plant that plays music or trying to look at what water does at different scales or, take different views of human disease, what have you, there's ways to ask questions. And the best way to ask a question, and I think we both strongly agree with this, is to ask a question such that the pathway to getting that answer is better than the answer itself. And that means that if you're going down that pathway, you cannot help but learn something. And of course it means that you need to stay alert and be aware of unexpected things that can happen. One example from my own science of quite a few years ago is we were trying to understand what happens in the chemistry of a circumstellar shell of a carbon star. So this is obviously a recent picture from the Webb telescope, but it makes the rather dramatic point that space is not just empty. There's actually a lot in space. These are what are called the pillars of creation, or the fingers of creation, or something like that. And so inside some of these dust clouds and parts of the interstellar medium are stars that are very, very carbon rich, and they're bombarded by radiation from high energy, like stars. And so they're constantly expelling carbonaceous materials as atoms into their circumstellar shell, where it cools off and the atoms begin to recondense and to form molecules. And it's got the kind of chemical mix that makes you think this is where perhaps things like amino acids or early building blocks for life may emerge from something like this. And so we were trying to understand the chemistry in that environment, and we had done a terrestrial experiment in a laboratory to try to emulate that. And this is what we found. We found that when you let carbon condense in a low temperature, low pressure environment, it condenses into the form of these molecules called buckyballs that have 60 carbon atoms in them and are shaped like a soccer ball. This was a completely unexpected result. It was so unexpected that when we were trying to explain our data, we actually had to go to art to understand it. We went to architectural books because there's no examples in the literature of chemistry of curved carbon. But there were lots of examples of architectural curvature, such as geodesic structures. And so these are called buckyballs because of Buckminster Fullerene. But just staying awake and asking a good question basically leads you to science that, and actually eventually, many years later, these things were found in space. But we didn't find them in space, someone else did.
Another example of persevering opportunistically, keeping going no matter what, is this exhibition. When I did the initial site visit for it, I was told that I could not hang anything from the ceiling. Well, maybe from the lighting tricks, but only 2 pounds. So I said, well, I'll make 2-pound art then. So these shapes hanging are actually styrofoam shapes covered with freeze-dried rose petals. And there are on the floor is a maze of rose petals. The show had 60,000 freeze-dried roses. It smells great.
So the lesson is, don't say you can't do something to Ginny.
Yeah. Well, if you want me, I'm just like a 2-year-old. If you want me to do something, tell me I can't. Here's another example of kind of the same thing, opportunistic perseverance. In this case, it was the museum itself that was the problem. The situation was I wanted to make a large sculpture, but this gallery in the museum was on the second floor. The museum has no loading dock or no elevator, and it's across the street from the White House, which had sharpshooters on the roof. So I had to figure out how to make something not too scary. So I made this 25-foot tall tornado in 3 parts like a slinky. And they're all squished up pretty good, and I put it together in the gallery and hung it, and hung 1,000 glass drops on it. And I didn't get shot or arrested.
So education is a pretty important part of both of our lives. I've run my group on graduate students and postdocs forever. I've taught classes. Ginny has people coming into her studio to learn art. And then we also make various efforts to teach art to the outside world or science to the outside world. And for science, that teaching to the outside world is a place where art actually becomes extremely important, because you can be dealing with something that's complicated on a scientific front, but if you want to make it relevant, you actually have to, and you know, many people will say, it's not about dumbing it down. That's an insult to people you're trying to teach to. It's about putting it in terms that can be broadly translated. And scientists are not good at that, but artists are actually really good at that. And the next slide just shows 2 examples of this. So this is pretty recent. It's about 10 months ago we published this paper in which we had studied 300 patients that had gotten COVID-19 and out through recovery. And we had found that when we diagnosed those patients, there were certain factors we could measure that anticipated whether they would develop chronic disease or not, and exactly what kind of chronic disease they would develop. And of course, this had a lot of implications. Long COVID now is a big thing, even as the pandemic has begun to subside a little bit. But on these patients, we had measured over 1 gigabyte of data per patient. It was staggering experimental effort and computational effort. Yet the message was to make it relevant to people who are concerned about this had to be fairly simple. So the left picture is something that Alison Kudla, our scientist, artist, and resident, who's here tonight, in fact, right there, put together, which I think tells a story better than the abstract of that paper or even the introduction of the paper could. You see COVID in the rearview mirror, but you have a bumpy road ahead. And that's exactly what we were talking about in this paper. And then on the right-hand side, this is the New York Times wrote up this paper, and this is the picture they used, which I think is a crazy good picture to describe the subject. it's actually one of our patients who got COVID early in the pandemic, and his road to recovery was very bumpy. In fact, he had awful nightmares every night for something like 6 or 9 months. But he eventually did recover. And his way of remembering that traumatic period in his life was to have this tattoo put on his arm, which does many things. The monster that came to him in his nightmares is the obvious monster you see in the tattoo, but the red on the bottom to the green on top is his journey to recovery. An amazing piece of art. Not something I would have put on my arm, but I think a remarkably concise way to tell a story that scientists would not have been able to do effectively. And I know, yeah.
When I started making art from glass, with it, actually the method that I use, it was only done by people in circuses, state fairs, shopping malls, and it was not taught at all, only handed down. Somebody would listen, and they were making these guileful things of wishing wells and swans and bongs. And I said to my students, how are we gonna change history if we keep making this stuff? Well, let's make something wonderful. And I had to kind of resort to telling them, if you make it, I'll break it. And it worked.
So a final lesson that we want to get across, and I think this is also relatively unique to science and art. We talked about these pathways that you want to go down, and you want to be awake, you want to have the opportunity to discover new things. But all this means, and this is why I guess I don't like the scientific method that's taught in schools, where you have a hypothesis, you go in, you test it, and you get an answer, because that tries to give you an efficient way to rationalize what scientists do. And science is intrinsically inefficient. And art is intrinsically inefficient as well. And in fact, there's no way to be an effective scientist unless you are willing to be inefficient, willing to ask dumb questions, willing to do dumb things until you finally work your... Science is self-cleansing in a way that art doesn't have to be, but it's only self-cleansing if you can ask those dumb questions, do the wrong experiments, and eventually emerge with the truth. And so I think an important thing that I try to teach my kids that come into my lab is, everybody wants to get a great paper, and they want to have a good CV when they go out and get a strong letter, but you don't do that by just going in the lab and following this prescription. You go in the lab, go after a hard problem with an interesting pathway, and be inefficient about it. But work hard.
Well, inefficiency are us.
Yes.
Making art is notoriously non-linear, and it works out better that way. If you make efficient art, what you're usually making is bad architecture. So now it's your turn, and remember, questions are a sign of intelligence when they hear questions. But remember,
You're really proud of yourself for that slide.
you're the buck who wanted in here.
so we're happy to answer questions. I think there's I don't know, there's microphones here and here. There may be a mechanism where you can actually write in a question to a chat. I think maybe that was instructed. And I don't know how all this works, but we're happy to really, it's not like this was a narrow subject that we talked about. Charlie.
If you want to ask it virtually, you can scan that code on the screen right there and type it in, and I'll read it out to Ginny and Jim.
I know, thanks, great show. I think it was worth the $5, so you only had to do $2.50 each. Question for both of you, and probably Ginny should answer first because you may go on, Jim. For either one of you, what have we learned to do differently because of the last 3 years, because of the pandemic we've been in as an artist, and Jim as a scientist? What have you learned to do things different in the future?
Well, that, my inner smartass always wants to think answers like, well, we can't wear lipstick under masks.
That's it?
Give me a minute.
Okay. Well, I think we learned on the scientific side a few things, and I hope those lessons will take. One thing we learned is that you can do systems biology in humans, which is not obvious before, meaning that you can measure a lot of things and put those pieces together in ways that I think were very surprising and enriching. During the pandemic, scientists, we all talk about how we collaborate, but there was a level of collaboration, a level of performance that I had never seen in science before. We launched our study and we filed the IRB on a Friday, and it was approved on a Monday. And by the end of that week, we were recruiting patients. We were sharing data with everybody around the world, and people were sharing data with us. We were shipping samples. We got things done amazingly efficiently. And out of that work, you had a vaccine come along. You had improved treatments for patients that were, when we started, it was like, Jesus, we don't know what we're dealing with here. You had antivirals that come out now that are now commonly given to patients. And we talked about, if you think about what a pharma company takes 20 years from concept to development to get a drug into the market, it takes 11 months. It doesn't mean there wasn't a lot of science behind that before, but things move very quickly. As the pandemic has ended, I do see old habits returning. And it is very disturbing. And I hope that, we don't. I actually hope we don't. I think we found new ways to do things, and I think it's exciting to do things in new ways. So we'll see, It's easy to slip back into old habits. But I hope we don't do it. And lipstick. Don't.
All right, we've got one from the crowd. If efficiency is the enemy, why is it so often the goal?
That's easy. Anything that's done, or most things, if they're done, efficiency is equated with doing it quicker and with less cost, and therefore more profit. That's my everything.
Also, as a scientist, you write grants, and you promise you're going to do something. And then it takes, a year later, the money comes, and I think many people actually feel, now we got to do what we said we were going to do. But you don't. You just need to be successful. Success makes everything go away. And so there's a tendency to try to be efficient. You said you're going to do something, to go and do it exactly the way you said you're going to do it. But in science, where the world evolves, you're not going to do it that way anymore a year later. You'd never do it that way anymore. So I've never really understood the drive for efficiency. I understand if you're a salesperson. But for science, I think it's counterproductive.
With art, it's almost an oxymoron. Efficient art.
Sounds like a good idea.
If you don't ask more questions, we're going to start asking you questions. And then you'll be sorry.
So you started out this talk by mentioning that you each ask each other what you've learned in the last week when you get together for poker. What have each of you learned in putting together this talk?
Well, I never have. I speak a lot, but usually just me. And I've not had to take into consideration pretty much anybody else's point of view. But it's been wonderful. We are good friends, so that was kind of the easy part.
And we're still friends.
Yeah. The evening's young.
Well, if you go to the ISB, we're on Terry Avenue in South Lake Union, and you go along the front, you'll see there's half a dozen of Ginny's sculptures there. It looks like a museum exhibit. And then throughout the building, we have more of them. I always thought they were proteins, but I came to find out that they're plants designed to play music and things like this. My perception of what she was doing was actually very different. And I think that's actually one of the beautiful things of art.
I always say when people ask, what is this? What did you mean? Well, whatever you see is there. There's no right or wrong in art. There is in science, but not in art.
Right. But I think we learned quite a bit. It was fun.
Yeah.
I have a quick question. Last night I was in a discussion with a colleague, and it was about original thought. Is there original thought? I know that we talk about original thought in art, original art, not derivative. Original thought in science is important to have original thought when you submit a grant application. But can you talk a little bit about that? Is there original thought in both of those fields? Or are we all derivative in some capacity? And in terms of the efficiency, I may relate to that question as well. I'm not sure.
Anybody who says that they are doing something or thinking something that nobody has done before is lying. And you don't make art alone. I don't think you make science alone. And there's nothing wrong with that at all.
We do occasionally find things that are original. Like when someone announces a high temperature superconductor and never had one before, that's original. Or when gravitational waves were first measured, I think that's an example of something original. But by and large, originality in science is connecting dots that already existed in different ways, and which I think is much of the story we were telling tonight. And so even the people who discovered high-temperature superconductors, were they trying to do that? Or were they connecting dots in ways that were new, and voila, something new came out? I think it's more likely that. Gravitational waves is a little different. I think those people actually were trying to measure gravitational waves, but there's a lot of people involved in that.
And you know that it's very collaborative, and also that gravitational waves are so, that's why they're very new to be found. They were predicted by Einstein in 1915. It just took us this long to find them.
Yeah. And I would argue along those lines that Planck, many of you all know, like the Planck, the first guy who actually thought things could be quantized, that was an original thought. And that changed the world, and no one really agreed, and he also didn't agree with a lot of that followed out of that. That was an original. So it does happen, but I don't think it's crazy common. I think it's very uncommon.
I just wanted to offer a few thoughts about this inefficiency and coming up with an answer at the end. Being a scientist and a little bit of artist, I paint. So what I find is that Jim is absolutely right. So you have to do silly things first. A lot of silly things, and people actually look at you. What are you doing? Why are you wasting your time? This is the way to do it. But deep inside, you know that these silly things that you are doing is almost like evolution in biology. So you can just imagine there are so many different organisms. They actually found a niche. How did they find a niche? They didn't actually follow a very specific direction. They were doing little things here and there. But when they found the niche, and now it's very easy for them to live in that environment. What Jim is saying is that when you do all these silly mistakes, you have to do silly mistakes and get there. When you get there, people look at you. I mean, I listened to Jim so many times. He gives a seminar as if it's so easy, right? So it's the same thing in painting. You know, I told my teacher, I want to do the simplest painting, which is color, watercolor. She said, that's the most difficult. You can't make a mistake. So you have to make a lot of mud. Then you learn how to actually control all those. I also want to say a little bit about Jim. Jim is the original, as far as I'm concerned, original inventor of nanotechnology. He's too modest to say that, but he actually discovered that buckyballs when he was a student. And I also agree with him that what he said, he's doing biology now, but he's a physicist. So, and I'm sure he has a lot of colleagues doing computational modeling and so on and so forth. When you combine all these fields, that's when you actually start discovering.
Thank you.
All right, we've got time for about 2 more questions, so I'll take some from online. Jim, it seems many scientists are also artists. How do you explain that?
Well, I'm a musician. I started off, I wanted to be a professional musician. I think the creative gene, if there's no, or learned or acquired, is actually very common, very much shared between artists. And I know many artists who are talented mathematicians and have a deep interest in science, like Ginny. I think it's the creative process that is attractive.
Yeah, hello. Thank you for the presentation. I really enjoyed it. I have a question for each one of you. To Jim first. So there was this very famous philosopher of science, Karl Popper, who said that that hypotheses are not derived from observations, they are tested by them. So there is a process in science, at least in as much as observations must always come later. They cannot precede hypotheses. But you said that there is no process. I would say that picking up on the blurb of the discussion today, on the blurb of the event today, that's where creativity is required. In science, creativity is required in proposing new hypotheses. So why would you say that there is no there is no process. I mean, don't you agree that hypotheses must always come before observations? And to Jenny, again,
Well, if your hypothesis, so let's just put in, because I'm going to forget your question by the time you get to Jenny's. It's a good point, but my hypothesis would be, I want to study this human condition, this disease state, what have you, because I think I will learn something. That really is my hypothesis. And I will take a broad swath at that condition, and I will try to see what the data tells me. And as soon as I begin to resolve what I think is going to be an interesting story, then you'll have to do hypotheses. If nothing else, the referee is going to come back and say, if this is right, you got to test this. But that's not how I start, other than that basic question, that this is an interesting thing to study, and we should try to study it. And it's worked. But I don't, maybe somewhere down the line as you're trying to parse that study out and give it to a graduate student, you may be a little more focused in your direction to them. But everybody does it differently. But I kind of think asking a general question with a good pathway out of that question is really more important than having a concrete hypothesis to begin with.
Okay. Thank you. To Jenny, the question again is about creativity. So again, Karl Popper said that in science, creativity is required to propose these bold, original hypotheses which have nothing to do with observations, foregoing observations. My question, it may be too broad, but that still is the question. What is creativity for in art? Is it art for just art's sake, and the creativity is not towards any purpose? Is it creativity to bring glory and glamour to the artist? What is the creativity for? I mean, so different artists have answered this in different ways, and I would like to hear your answer to this.
Well, creativity, I think, is, bottom line, problem solving. And you have different problems. You give yourself different issues. I mean, they can be problems like, which route am I going to drive to work today? Or it can be, how am I going to paint this canvas? But I think, to me, creativity in art just means approaching figuring out how you want to say whatever it is that you want to say. It's a hard one. It can be figuring out the best way to say what you want to say. Or it can be just figuring out what you want to say. And it depends on the person, on the artist. It's not a very good answer, but...
All right, we'll have one last question. I think this is a nice one to end on. I'll make it a little less vague. How in the last year, sort of coming back to living life a little bit more normally, where have you been finding your new inspiration in this sort of new normal?
Friends. Friends and finding new ways to spend time together and realizing how wonderful their company is that's really inspiring.
Yeah, I think there's no shortage of places to find ideas now. The world changed in many ways. Hopefully we're going to, a couple of years down the line, we're going to look back and say it was a very difficult time, but we came out better. And I think there's a lot of opportunities. I think having the patients that participated in the studies that we did allowed us to begin resolving chronic disease. That's a crazy hard thing to do. And I think we now actually have signal to begin thinking about that. And we simply didn't before. Because you can't do it with 10 or 20 patients. You need hundreds of patients. The tools that we have now, you can resolve the heterogeneity of biology. It's been confounding us since the beginning of biology. Now it's gone. You can resolve the heterogeneity of biology. I think there's no lack of inspiration for doing new things right now. I'm an optimistic person. Otherwise I wouldn't be a scientist. But I think that's yeah. You always have to think it's going to be better. And of course, friends. Ginny always pushes.
It is always going to be better.
Well, what a great note to end it on. Thank you so much, both of you, for being here. And thank all of you for coming.